Alright, so this eighth section here is the last one for material for exam 1. So I just want to start out by reminding everybody that exam 1, everything 1 through 8 is fair game, but 1 is, it's like class details, so it's really more like 2 through 8 in terms of actual class content. So just a reminder on that. So at the end of this, series of videos, when we're done with this section here, that's the end of what's fair game for exam 1 in terms of the content you're expected to know. Now, there's probably more sections you have to do this week, but they're not going to be on the test. So that next section, section 9, will begin material for exam 2. So just a reminder on that. All right, so in this 8th section, we're going to talk about organic chemistry. And to start out with that, we're going to talk about chemistry of carbon. So organic chemistry there's a number of ways to define it. Let me just preface it by saying this, and they all are flawed. There's no perfect definition, but there's a certain beauty in simplicity. So the good simple definition that's pretty spot on is just that organic chemistry is, so it's not about like vegetables or anything like that. They stole our word. We had organic first. Stupid farmers, they get everything they want, I tell you. So organic chemistry is the chemistry of carbon-based molecules. It's not a perfect definition. There are some carbon-based molecules that might not be considered organic, but it works. It's a good start. For this class, it works beautifully. So, how are we going to talk about organic chemistry? Well, let's talk about the chemistry of carbon to kick it off. So there's going to be a few videos we do, a few different pieces to this. But to start out, let's talk about carbon, because that's the key element in all this. This is the element that drives organic chemistry. So remember, looking at our periodic table, we can see a couple details about carbon. The big one is that it makes 4 bonds. And this is going to give it the ability to be very versatile. The other thing is, like, silicone makes 4 bonds as well. It's right below on the periodic table, but it's much heavier. So carbon is light, plentiful in the Earth's environment, and it makes 4 bonds, which makes it very versatile in terms of chemical bonding structures. And so you can get a couple things that can happen with carbon right off the bat. So you can get 4 single bonds. On a carbon. So I'm just drawing the bonds. I'm not saying where they go to. I'm just drawing, rough bonds. So maybe they're hydrogens or other carbons, or who knows. You can get a double with 2 single bonds. All right. And we can also get 2 double bonds. So you might have seen something like this in like CO2 when we were talking about that earlier. And then carbon can also do 1 triple and 1 single bond. So there are always 8 bonding electrons around carbon. Now you can see that. There are always 8 bonding electrons around carbon. And so you can go 4 singles, double, single, single, double, double, triple, single. You can't do like a triple double because that would be 5 bonds, right? You can only make 4. So no 5s, only 4s. So we can get a triple plus single bond. So carbon's very versatile. These are all different, chemical things it can do. Different bonding structures. These all behave very different chemically. And in addition to this is where carbon really takes off as the basis of organic chemistry. So 1, it's very versatile, it's light, very functional, very available. If all of life's going to be based off of an element, it should be a pretty common element, right? We don't want to all be based on, plutonium, which doesn't even occur naturally, because then how do we come about, right? How does life get formed? How do you need more plutonium to have offspring. Where does that plutonium come from? So carbon is everywhere. It's in the atmosphere. It's in all the other living organisms around us. It's in minerals sometimes. um, carbonate compounds. So there's a polyatomic ion, carbonate, that's based on carbon, and so that's one way that carbon can be in the environment, as well as like CO2, and well, now that plants are making them, starches and sugars, fats, oils, things like that. So very available, lightweight, which is good. We don't want to be any heavier than we have to be, right? We're already heavy enough in this country. I know that this, being stuck at home thing hasn't helped me out any in that regard. I hope you guys are doing better. And the other thing is, carbon can start bonding with carbons and making chains. And generally in an organic compound, we'll have hydrogen on there too. So it can form chains, and often does. Gasoline is just a mixture of carbon chains, all somewhere around approximately 8 long, capped off with hydrogens. So, the bond has to go somewhere, and more often than not in organic compounds, it goes to hydrogen. And so this is an example of 1, 2, 3, 4, 5, 6, 5. So this would be called pentane. You do not have to know these names. I just like to flash my skills. That would be the name of it. There's a whole naming system we don't have to learn. But if you take organic chemistry, which you definitely do. So it can form chains, and you can get different lengths. So plastic, like my marker here is made out of, at least the body of it, is actually carbon chains that are long, like hundreds or thousands of carbons long, depending on what plastic it is. And how those chains are put together also determines what type of plastic it is. But they are long, and then they sort of are spaghetti noodles stuck together. And that's what makes them a solid. They have a ton of interactions with their neighbors, makes them a solid. We'll talk more about that later. But plastic is carbon-based, and it's extremely long carbon chains. So that's what makes it so much lighter than something like a metal, is carbons tend to be lighter than metals. If we look at our periodic table, we can see carbon weighs less than, say, iron, or even aluminum. So that shows up. So that's why plastics are such a nice, light, versatile material. Plus we have currently a ton of carbon that we can access to make these plastics. So they're also cheaper in that regard as well. Now that might not always be the case, but it is right now. So we can get these chains, and then we can also have things like branches on these chains. So branches can come off of the chains. Can't spell. We'll say chains can branch as well, or have branches. I really can't spell that word today. All right, there we go. All right. It's because I'm filming on a Friday. End of the week, It's been a long week, I guess. So we have a 5-carbon backbone like before. So often we call this like a main chain or a backbone, but then there's a branch off of that main chain. Now, all of these carbons still need to make 4 bonds. So that's a good, what I call a chemical instinct to keep in mind. If you don't see carbon making 4 bonds, something is wrong. There always is 4 bonds around carbon. All right? And so to keep it simple, we're just going to keep putting hydrogen on here. So, if you've ever done any sort of plumbing, you could think of carbon as like the pipes, and then all these hydrogens are like caps or fixtures or whatever you're connected to. They're endpoints for the plumbing. So that is where your line terminates, or they're like train lines. These are terminals that don't carry through to other stations. A few different ways of looking at it. But we can have these chains, we can have branches, and then another thing carbon can do is it can form rings. So we gotta make sure we have 4 bonds around here, so I'm gonna still put 2 hydrogens on each of these carbons. A little creative at the bottom one here. So fill out this whole molecule. And what we have is a 6-member ring. And so this is called cyclohexane. By the way, this guy, it would be 1, 2, 3. So it would be 3-methyl pentane. But carbon can also form rings, and these rings can connect to chains. So like all these pieces can be put together. Carbons can always connect to other carbons. And this could be connected to 3 other carbons potentially, or 4. That can happen. So it's very versatile. That's really the point I'm trying to get across here. And I'm showing it to you. And I'm showing it to you with these Lewis drawings. So, in addition, we can mix in things like double and triple bonds. So you can have a chain of carbons. Everything I've shown so far had single bonded carbons. But we can also have double bonded. And again, everything I'm going to draw for a little while here is going to be carbon and hydrogen. Alright, so we have a double bond in our chain. Carbon's still making 4 bonds here. 1, 2, 3, 4. This one's also making 4 bonds. 1, 2, 3, 4. And then, over here we have the classic 1, 2, 3, 4. 4 single bonds. So just note that chains can also contain double and triple bonds. Now you don't often see triple bonds in a ring structure. Not saying it can't happen, it just tends not to naturally happen very often. But you see double bonds quite a bit. So someone draw that same 6-member ring before, and now I'm going to alternate. Every other bond between carbons will be double, single, double, single, double, single. And so that means every carbon has 1 bond left over that will go to a hydrogen. And this is known as benzene, so this is an incredibly important and common chemical. It used to be used in a lot of reactions, and then it turned out that it causes cancer. People started finding out this sort of thing about a lot of different compounds over the last 30 years or so. The interesting thing about benzene is it's flat. So it has a flat geometry. Due to the fact that you have the double single bonds, it's like a pancake. There's no bending or anything. It is locked into a rigid hexagon shape that is flat as a pancake with hydrogen sticking out flat. And so it just you just flip it. It doesn't flex. It's all you can do. So it's a very crisp pancake. And it's the exact right size that it can fit in between the bases of DNA. And it will just slide in there and interact with those base pairings and interfere with things like DNA replication and transcription, so that you start having issues, and those issues can become very serious, like cancer. So benzene quickly went from being a darling solvent to one that we just don't use anymore. I had a professor who was a theoretician. He taught physical chemistry at Oregon State. I had physical chemistry class with him as an undergraduate. And he said he told the story, the only experiment I ever did was, and so we're all chemistry majors in this class by this point, by the way. It's like a 400 level class. And he's explaining, I only ever did one experiment, and I had to find essentially how plastics moved over time. So it's the diffusion rate of plastics would be the technical term, but it's just basically how do plastics slowly change over time. Like if you ever see a window that's really old, the glass gets ripply, that's because the glass is moving over time. Plastics will do the same thing, but it's very slow, just like the glass. And so to observe that as a graduate student, you want to see it happen in a couple weeks, couple months maybe. You definitely don't want to wait 20 years to get your degree, so you got to speed it up. So what he did was he put it in solvent. He put it in a solvent to help kind of accelerate this process, and then he could kind of scale it back to if the plastic was alone, or so he was thinking. It turned out it wasn't a very good idea all around, but what made it a really bad idea was the solvent he used was benzene, and it was before everyone knew it was cancerous. And as soon as he said that, the entire class, just everyone's hands were in their heads. or your heads were in their hands, or they were laughing, just in disbelief. And he looks out of the class. He's like, we didn't know it was bad. All right. He's like, and the worst part was my office had no ventilation. It was basically just a closet. So he's basically sitting in a closet with a huge beaker of cancerous solvent that is evaporating. He said he had a lid on it. It wasn't a very good lid, but he had a lid, so that helped. Um, he definitely seemed to be in good health, and he wasn't no spring chicken by the time I had class with him. I'll say that. Great guy, but it appeared not to have any adverse health effects, which is good. But it was a definite risk he took unknowingly. And so, as time goes on, we tend to learn more about substances often, and this was a big one. So now there's really strict requirements about how much can be in things like gasoline, because it is a naturally occurring hydrocarbon. When you drill for oil and you extract it and you make gas, generally what you're doing is you're just getting stuff that evaporates at a certain temperature. We call that gasoline. So it's carbon chains, but it's not like it's this specific carbon chain. It's just a mixture that has the right overall physical property. And benzene tends to slip into that range a lot. And so now they have to test gas because it's so stable, it often will burn when it goes through a car. Now, newer engines, they run leaner and hotter, and they can actually do that. But like older cars, benzene in, benzene out. That was a big concern. And when you have cities full of cars just belching this stuff, it was statistically probably a bump in the cancer rates. Not huge. It wasn't like everybody was getting it, obviously, but a couple tenths of a percent jump or percent jump, that can be statistically significant in a large population. So, really, I always get off on a tangent on benzene. It's a very interesting molecule. But all I really want to show is just that, rings can also have double bonds. All right. And triple as well, but not common. I'm not aware of a lot of triple bonds in rings. There's a geometry issue with that we're not going to talk about, but it's theoretically possible. In reality, it doesn't come up very often. It would be a very unhappy, extremely reactive molecule. So, this is what makes carbon so versatile. It can do all these different things. And it can scale up to thousands of carbons along in the chain, branches and ring structures and all this stuff, all carbon-based. And there can be hydrogen, and there can also be other elements as well, like oxygen and nitrogen. We'll talk more about those at the end of this section. And you can also have like halogens, which can be some very, very dangerous chemicals because they tend not to show up in nature, but they tend to be similar to things that do. And that's often where you encounter a large hazard. So this is a very interesting one because it's not really like anything else, but it's just like a lock and key situation. It just fits so nicely in that DNA. That's really uncommon. So I threw it out there. It's like the first thing you heard of, so you might think, oh, that might happen a lot. Like, no, this is a pretty interesting one. Like it's just the perfect molecule to do that. It's so simple. All right. So next, we're going to talk about some easier ways to draw these molecules. I've kept them short for a reason. I didn't really go over 5 or 6 carbons because this is a lot of work compared to what we're going to do next. There are easier ways to draw these because chemists are lazy. We create shortcuts and then we stick to them. So I'm going to show you some shortcuts, and then that's going to be basically how I draw all the molecules for the rest of this section. So just a heads up on that.